Now the question is that is it really efficient that I could take in a flight from San Francisco in a forward search to any airport. I did solve it in a backward search by saying that let it be a specific variable. I later on tried to do all kinds of permutations and combinations of over all the substitution. That's a simpler problem. And if I do get that, most of them will get heavily constrained, so there'll only be one which will be remaining, and that'll be obvious when you look at the source. Is it really efficient? And the answer is obviously no. It's still a classic search, and in order to improve it, we need in a backward search, of course, what is called as the heuristics. So we need to add in some kind of a heuristics into it, only then it will become a good search. Now, when I was discussing heuristics as in the A star, which is exactly the algorithm we're going, I told you a lot that this problem, this heuristic, this problem, this heuristic. I even said I cannot tell you in general what is a good heuristic function. Now I can. It's a generalized representation. My state is nothing but an array, a linked list of Boolean variables which are known to be true. If they're not there, they are false. And for that, let us write down what is a good heuristic function. So with the heuristic function, of course, I will make a function hs which tries to find distance of S to goal, and let's start doing it. I'll do it by the relaxed problem method, which means I will relax some constraints. Okay, so let us take a very quick example dummy problem. So let us say that I have actions, dummy names A1, A2, and A3. And in this, let's say that there is some preconditions. So something like X and Y and not Z, X and Z and B, and not X and Y and Z, or something like that. And the effects are around over here. So let's say this is, it produces A, it produces B, it produces C and P and Q and whatever, R and S and T. So now what I do around over here is that I do have some souls. Let us say that is F and G, and everything else is negative, and I do have to reach around for a goal, say that's F and A and B and C. So F is already obtained from the source itself. How much efforts do I need to go towards A, B, and C? I cannot really say because there are conditions to be taken care about, and if I really go up in giving you a closed form direct mathematical expression, it will be the entire search, which is going to take time. So let's apply some relaxation and let's relax a constraint. So the relaxation that I apply is that I say there is no precondition. Of course, I'll have to relax something so that I can give you a quick to compute solution, and the only effect. So what you see around here is how do I get A by A1, how do I get B is by A2, how do I get C is by A3, and therefore my heuristic is nothing but the number of sub-goals that are not yet satisfied. And that's the quickest to compute, so you could easily compute that up. That's a simple exercise. But then I have made other additional assumptions around over here, and there are two bad assumptions that I made around over here. So let me write the assumptions down one by one. The second assumption that I made over here was that every action was giving me one sub-goal. It's called as the assumption of sub-goal independence, which simply states that there is no action that attains two sub-goals directly. We saw that previously. So to get a parcel at John F. Kennedy, I did not magically get the other parcel at San Francisco. It had to be done by its own set of actions. So you did not see that two sub-goals were getting satisfied simultaneously. So if I need to violate that assumption, I just add a and C. Now the heuristic cost, which was earlier 3, will now become 2. So earlier it was A1 and A2 and A3 in any order. Preconditions have been removed. We'll get A and B and C. Now it's just 2. Because A1 gets you A and C, what is remaining is B that A2 gives you. Or after with sub-goal independence, the answer is 3. However, without sub-goal independence, one action can get you 2 sub-goals. The answer is just 2. So I assume sub-goal independence, so let me remove it. And the third one is a related one, and it is no interaction of negative goals. So the problem is that if I add, instead of and C, not C here, and let's say not A here, I still apply A1, A2, A3. If I apply A1, no precondition, I do get A, but I also get a not C. That's negating what I get into the goal. If I then apply A2, of course I get a B. If I apply A3, I do get C, but my A is undone. It's unachieved. Or a goal that I achieved earlier is now removed. So it does not matter in which order you apply them. One is undoing the effects of the other, and therefore my answer is again not 3. I'll have to look at some other actions and see what can be done about it. So I made these 2 assumptions. Now, if you make these 3 assumptions, no precondition, sub-goal independence, and action achieves a maximum of 1 sub-goal, and no negative interaction, then the number of sub-goals is the heuristic. Now what I'll do is, I will remove one of the assumptions. Let's remove sub-goal independence. There's still no negative interaction, so now I can have 2 sub-goals at the same time. So this also gives me C, and let us say this also gives me B. And the question is now, what's the solution? Answer is due intuitively, but what's the program? So let's visualize this up. The unmet sub-goals are A and B and C, and let's write down all the other sub-goals. A, P, Q, B, R, S, C, T, B, C, T, and B. So these are my sub-goals. These are not sub-goals, these are all the variables possibles. So action 1 produces A, P, Q, C, A, P, Q, and C. So that's action 1. Action 2 produces BRS. and action tree produces CTB, and I need to be able to produce A, B, C which are unmet. So A, B, C which are unmet. The answer is, of course, I'll have to select sets A1 and A3. In general, it is called as a set cover problem, which we will not be discussing around here. I've given you the standard name. The problem is set cover problem is NP hard, but then there are good greedy solutions to it, which do the task in polynomial time. And of course, they are greedy. They may not be the best, but then we are discussing heuristics. Now we'll start compromising optimality to our computation cost to good heuristic value. You've already seen that we do not have actions which have cost. We are discussing the oldest version of PDDL, which is called as the planning domain definition language. We are at version 1. Version 1, there wasn't any action cost or optimality in that constraint. So flying from John F. Kennedy to San Francisco had the same cost as loading a parcel into John F. Kennedy. In reality, the costs are terribly high. One would take in somewhere around $500,000. The other one is just less than $10. Oh God, I have to give example. I took example in dollars, so I have to give cost estimates in dollars. So a greedy is good enough for us. It may have a little bit of assumptions, but it is good enough for us. Now what I'll do is that, of course, that's one good heuristic function, but then practically the problem that happens with all the set cover and all is the fact that it returns you extremely small value, and because it returns you extremely small value, what really happens around is the fact that the heuristic function saves you a little time, but that's not good enough. So comes around the other options, that what could I do in order to solve the same heuristic problem. And now I'll just start getting informals. I'll just dictate that up. So another thing that you could do is that you could apply another relaxation. In planning problems, what happens, it would have been very simple, but then the problem is that the negative effects, they undo what you previously done, and these negative interactions, they cause you to do quite a lot of work. Otherwise, the planning problem has very small depth. It's naively solvable. So I remove only the negative effects. Unfortunately, that's another problem, and this problem is also not very easy to solve. But then again, what really happens if you remove the negative effects, it is solvable by a class of algorithms which are called as local algorithms. So local algorithm is, you just, instead of generating a tree and saying 10 actions possible till depth 1, next every parent can give rise to 10 children, that means 100 actions possible, you just say that let me select anyone randomly and then anyone randomly and then anyone randomly, and you will reach the goal. And that's a very popular heuristic wherein I remove the negative effect so that the actions won't catch each other's effect out, and then I apply a local search and solve my problem. Local search is the other code, so I did not touch anything up so far. There's also a state abstraction, so you could drop in variables which throughout, so you could drop in variables which you believe after dropping give you a smaller problem. So like this cargo thing, a cargo needs to go from one place to the other. You could say they are infinite planes, and hence the planes are not even important now. You could say that, okay, anything can fly from anywhere to anywhere, and of course, that is exactly what you would have assumed, that the heuristic value is 3 times load, unload, fly, the number of cargo that you need to send. That's a strong heuristic. And you go upon saying that, okay, I can remove the airports, I can remove the planes, I can remove specific constraints, like in the blocks world, where one block had to be moved in and you had to make in a nice little structure. You could say that the clear assumption is removed, so there is no clear. Everything will be assumed to be always clear. You remove in state variables, that's going into the abstraction that we discussed previously. Or you could just say that I will go with sub-goal independence, and the moment sub-goal independence is there, then your problem of attaining G1 and G2 all the way up to Gn is just attaining G1. How do I attain G1? It's a very small problem. So how, in which cost can I attain G1? It's at C1. How can I attain G2? That's at cost C2. And all the way, just add them up, and attaining G1 and G2 and Gn is a difficult problem. But how do I attain G1? That's a very simple problem. You could just do a full-fledged search, only how to get G1, and just add up the costs. The point that I made around over here was interesting one, that we did not discuss anything which is, any heuristic which is specific to the problem, like in the A star previously. Everything is much generic. And because it's generic, you could just load a planning library which comes with all these heuristics in place. Given your problem specific, you would not even have to supply with a heuristic function. Of course, in research, we would still use heuristics, but that's how we model the problem at the first place. Not unnecessarily variable, not too many variables, actions which are more guiding, those are separate heuristics. But in principle, we don't need to supply any heuristic. The algorithm will have it, and that's because we're no longer doing generic variables, we're doing specific propositional logic variables, where all these heuristics are, like the constraint satisfaction problem, already embedded into the generic programming methodology.